So what I basically was saying that I'm going to talk in this talk about the specific challenges that are that classical statistical techniques face with when they try to deal with real-world problems, and they involve massive scale of data sets, diverse information, and sparsity, which the sparse algorithm, which both have important consequences both for interpretability of the algorithm, but also for economical cost, and I'll talk a bit more about that later. But so basically what I want to do first to start off with is what I've been personally strongly interested in, which is this heterogeneous data manipulation. So basically just, let's look at an example here. For example, you want to classify web pages according to their topic, and this just happens to be very relevant here not to this audience, but I kind of use this example very often actually. So you want to do that classification where basically one data point is a web page and you want to predict whether it's about politics or sports or something else. Now what you can use to classify this web page is all kinds of information. You could look at the text which is available in that web page, but maybe the images present in that web page might also tell you something about that. It might be the specific HTML structure of the web page. There might be sounds present in the web page. Also, you might know something about the link structure of the web, which tells you which web pages this page is linked to, and you might want to use that information to predict the topic of the web page. Or you might have log data about users coming into the web page, know which domain they actually come from, and know which link they use to actually leave the web page. So if you want to use all that type of information now to make predictions about the topic of the web page, then it's obvious that it's not going to be just a classical statistical task where we have one big vector of numbers which then will be classified into one or another class, but we actually have information in very diverse formats, which is not necessarily numerical anymore, and we have to try to deal with that and use all that information that we have available to make that prediction. Okay. So on top of that, this is a massive task because obviously there's a lot of web pages out there that we want to try to deal with. This is another example of a research topic that I recently got involved in. But so basically imagine that we look at music and we would like to basically jointly model audio content of music and words describing the music. And so why would we like to do that? Well, one of the reasons could be to build a joint statistical model of those two, such that when you're basically giving a query in words about a certain type of music you would like to see. For example, imagine you would like to see a rock song which is somehow romantic with drums and guitars. Then you would like to build an automatic system that pulls out from a library of songs based on purely the audio, the songs that actually reflect what you want to listen to. Not because there is text around that song that actually says rock or romantic or guitar or drums, but really because the audio content really reflects the features of drums, of guitar, of romantic songs. So what we're trying to do here is basically build a joint model for very heterogeneous data, heterogeneous descriptions of the same song, the audio content and a review of the song. And so by building that joint model, we try to do what I just described, which could be, annotation of new songs or the inverse, basically given a query, retrieve songs from a database that actually match that description based on the audio content of the song. Sparsity is obviously important here because, when we do this annotation, we just want to have a small set of words that are most relevant per song. This is another example of an application that I've been working on quite a lot in the last 3 to 4 years in computational biology. So imagine, for example, that we're looking at an animal or a human being, and we're looking at a whole bunch of genes or proteins there, and we try to predict what is the function of those genes or proteins. Then there's a whole diversity of information again that we can use to try to make those predictions. We can basically expose those genes to different experimental circumstances and measure whether they are up or down regulated. So basically we obtain the so-called microarray data, which gives us under different experimental circumstances a reading for each of those genes or proteins. And so that is obviously very numerical data because every color here can be translated into some kind of number which tells us whether the gene is up or down regulated. But something very different from that numerical type of information could be when we know what is the amino acid sequence corresponding to a protein, which is basically just a sequence of letters, all right, from a certain alphabet. Or we might have information about how the proteins that we try to predict the function of interact with other proteins in that metabolism in that animal or in the human being. So we might also have information about how the hydrophobicity of the different amino acids varies with the length of the protein here. But again, the bottom line is we don't have just a vector of numbers that we try to classify. We here again have a diversity of information that we try to use and integrate now to predict what is the function of a specific gene or a specific protein, all right? And so again, sparsity could be important here because Imagine for the biologist that we could tell him afterwards, well, the interaction information and the sequence information is very important to predict the function, but microarray data, forget about it. It's very interesting for the biologist for interpretation reasons to know that, but also financially it's important because deriving microarray data costs a lot of money, okay? So again, coming up with a sparse algorithm, selecting which information sources are important is an important step here. So what I'm going to try to do in this talk is basically cover some of these challenges that I mentioned before, including the diversity of information one that I just talked about a little bit, by giving two examples of problems that I worked on. One of them is specifically classification algorithms for dealing with heterogeneous information sources. And then there's a second one on sparse principal component analysis, which mainly deals with these sparse type of algorithms. So to talk about the first one, I'll first give a short introduction on basically the philosophy behind kernel methods. I'm just wondering here, how many amongst you are familiar with what kernel methods basically do? Okay, so most of you, it seems like. So basically, after that introduction, then I'll kind of talk about what I've contributed in the field myself and what I think is a good approach to deal with these heterogeneous information sources. So basically, in kernel-based learning, what we do is we embed data and data points here, x1 through xn, in a high-dimensional Euclidean space. And the important part here is that each of these data points that we're looking at is actually described by some piece of information, which is this green ellipse here. But that piece of information could be anything. It could be the address of a person. It could be the sex of a person. It could be, how basically web pages are linked to other web pages. It doesn't need to be numerical information per se. It's just some type of information which we then use to come up with this high-dimensional Euclidean embedding. And then once we have that embedding, we run some linear algorithm, a classical statistical algorithm in that high-dimensional space, corresponding to a whole bunch of acronyms, all depending on what kind of data analysis we want to do. And basically, from that data analysis, we can then find the patterns that we want. Now, the thing here is, basically, the reason why this kernel-based learning came up 10, 15 years ago was if this data is actually described by numerical vectors here, then this step here, this embedding step, could correspond to a highly nonlinear transformation, which basically corresponds to giving us the possibility now to come up with a nonlinear algorithm here, because obviously finding a linear algorithm in this high-dimensional space here will correspond to a nonlinear relationship between the data points in the original space here, all right? And this was really the original motivation of this kernel-based learning framework to come up with nonlinear versions of linear algorithms. Now, recently, in the last 5, 6 years, let's say, people have noticed that defining such an embedding can also be done for non-numerical information. And so basically, it gives us a handle to deal with data that is more diverse, that is not described by numbers anymore, which is basically a type of data that classical statistical algorithms had trouble dealing with because they always worked on numerical vectors, basically. Now, the basic thought of this kernel-based learning framework here is that the embedding of these data points, which we can denote by phi of xi, phi of xj here, so basically this is this high-dimensional Euclidean space, this embedding is actually not explicitly defined, so we will never explicitly specify the coordinates in this high-dimensional space here. What we'll do instead is we'll basically implicitly define the embedding by mentioning the inner products between each pair of data points in this space here, all right? And those inner products can somehow also be interpreted as some kind of measure of similarity between pairs of data points, which is an interesting interpretation to just easily understand this framework in a more general setting. Now, to define this inner product in this high-dimensional space, one can either use this so-called kernel function, which basically just defines the inner product between each pair of data points, xi, xj, or you can basically also define what's called a kernel matrix, which is basically a matrix that has as many rows as there is data points, and as many columns as there is data points. And then one specific entry in this matrix, let's say on row I and row j, gives you what is the similarity measure or the inner product between the image of the ith and the jth data point in this high-dimensional space here, okay? So basically, this matrix contains all the inner product information or similarity measures between each pair of data points in this space here, and therefore implicitly defines this entire embedding here, again, without explicitly saying what are the coordinates of the embedded data points over there. Now, the thing is in this kernel-based learning framework that most creativity now needs to come at the stage where this kernel matrix needs to be defined or derived from the information that you have. And when you can do that in such a way that most of the information that you have about the data is contained in that kernel matrix, then you can actually expect that you have an embedding that reflects very well the information at hand, and therefore, you can have a successful linear algorithm that you apply afterwards. Now, to design this kernel matrix here, basically, you can be very, very free in your creativity. The only thing you have to make sure is that it's a positive semi-definite matrix, which means eigenvalue is positive, to ensure that it actually corresponds to, implicitly, to some underlying high-dimensional embedding. Okay, so again, this kernel-based learning framework, what it basically does is it has these two modules in it intrinsically, where first we define the embedding of our data in this high-dimensional space by basically designing the kernel matrix. Then in the next stage, we only use the information in this matrix here to run some type of linear algorithm to extract patterns from the data. And so basically, those two phases can happen independently. You can design all types of kernels for different types of informations, and then you can basically design all types of algorithms for different tasks, and you can just mix and match between the two. So this framework is actually applied for a variety of tasks in machine learning for dimensionality reduction, clustering, and so on. The task that I'm going to focus on here is specifically classification. And for that task, there's been many successful applications, in text classification, phase detection, and so on. But anyways, let me just talk about the specific task that I want to focus on here, which is binary classification. So basically, let's assume we have n training data points where xi is a description of the ith object, and where yi tells us whether it is, in a class -1 or a class +1. So it's basically a member of either of two classes. That's why it's binary classification. Important to realize again here is that xi is a description of the ith object. Okay, so this description again can be numerical, but it doesn't necessarily need to be numerical here at this stage. Okay, for example, xi could be the file about a patient, and then we could know about these patients whether they are actually ill, class -1, or whether they're happy because they're healthy and they're so in the class +1 here. Anyway, so the challenge here is, can we now design a classification rule such that given a new xi, we can actually predict the label yi with minimal probability of error? That's really what it's all about in binary classification. And so one of the ways to address this problem could be to, first of all, try to represent our data again in this high-dimensional space, the kernel-based approach. I mean, in general, you could do also when you just have numerical vectors, you could try to represent things like this. And so one of the ways to go could then be to try to separate these two classes of training data points, which are here represented by, let's say, the green dots for the class -1 and the red dots for the class +1. Let's just try to find some hyperplane that separates those both classes, okay, defined by some parameters w and b. And once we find that hyperplane, we basically have a classification rule to classify future data by just looking on which side of the hyperplane a new data point comes. Okay, so imagine we get some new data point which basically comes here in the space. Well, then we decide it's actually part of the green class, right? So which basically just corresponds to the mathematical formula down there. So anyway, so one specific algorithm known as support vector machines or maximal margin classifiers will now position this margin in such a way between the two classes, the -1 class and the +1 class, such that the distance or the two-norm distance to the closest point from each class is maximized. Okay, so there's obviously different ways that you can position this hyperplane here, but this is a very specific algorithm that will try to do it in such a way that the margin between the two classes is maximized. So basically, this distance here is try to be maximized. So now you can obviously say, like, when those classes are not separable, what can you do then? Well, if they're not linearly separable, we can introduce some slack variables xi I, which allow some of these data points to be actually inside the margin, like this one here, or on the other side of the margin. Okay, so we allow ourselves to make some errors, and then basically we try to maximize, besides that, the margin for the data points that have no error. Okay, by introducing these slack variables xi I. So now, without going through any math here, let me just formulate what is the final mathematical formulation of this specific algorithm here. Basically, in order to find that hyperplane, we have to solve an optimization problem to find the optimal position of that hyperplane. And it turns out that that optimization problem has two terms in it. One term, as we said, corresponding to maximizing the margin, and the other term, which it's traded off against, is a term where we try to minimize, obviously, the error. We want as few points as possible to, commit those errors here. And so the constraints to which this optimization problem is subjected is just that we try to impose the fact that most of those data points are correctly classified, which is the red part here. And if that's not possible, then we allow some error slack, which we here try to minimize. Okay. Most important about this is if you look at this optimization problem, these constraints are just linear constraints, very simple to deal with. The objective has a square here and a linear term here. So it's basically a so-called quadratic programming problem, which brings us in the class of convex optimization problems, which are basically nicely conditioned problems that are quite easy to solve. And also they have one global optimum, so we don't have to deal with local optima when optimizing this, which means that the results are reproducible. So again, it's basically an optimization problem that we can solve quite easily, also for larger scales. To analyze the problem a little bit more, we derive what's called the dual problem. Now, without going into any detail again here, the dual problem actually is some kind of sister problem, which we can derive for any type of optimization problem. And what it does for us, it gives us additional insight into the problem, and maybe also some kind of alternative formulation which is easier to solve. Okay? Now, the insight it's going to give us here is the following. So if we derive it, it turns out it's actually a maximization problem over some variables alpha. And there's as many alphas here as there is data points. Okay, don't worry why that is, but that's just the case here. Now, the main thing to point out about this dual problem is that the way the data points appear is through the inner product, phi xi transpose times phi xj, all right? And so basically it turns out that if we know these inner products, and obviously also the labels yi here, we can actually entirely formulate and also solve this problem here, which basically means that if we know the kernel matrix K, which is the matrix that contains all these inner products, and we know the label information, that we can actually solve this maximal margin classification problem, all right? And so the nice thing about this is that this observation makes this algorithm entirely fit in the kernel-based learning framework, because kernel matrix and labels is enough to actually train the classifier, meaning find that hyperplane, okay? There's something else now. If we derive this problem here, this dual problem, then on the way to get there, we pass by an optimality condition, which basically defines the relationship between W, which is the parameter of that hyperplane, and alpha, which is the variables of this sister optimization problem, let's say, the dual. Okay, and now using that result allows us to derive one more thing here, which is if we want to classify a new data point x, we need to evaluate this formula here, basically to see on which side of the hyperplane it falls. Now, by substituting this result for W in here, we notice one important thing again, which is that to classify a new data point, the only thing we again need to be able to is evaluate the inner product between basically all the phi xi's, the training data points, and this new data point phi of x here. So again, by knowing the inner product information, or the kernel function between all the training data points xi and this new data point x here, we can actually now also evaluate the classification rule and classify new data points. So bottom line here is we can train, fit the hyperplane, and evaluate our classifier, meaning make predictions for future data points, entirely when we know this kernel matrix or inner product information or similarity information. So as I said, this basically makes this algorithm fit entirely in the kernel-based learning framework, because this matrix is enough to do anything we want afterwards. And in this case, the algorithm that we apply for classification is also known as support vector machine. So this basically brings us at the end of the introduction. Now, what I want to do now with this learning framework here at this point is try to use it to deal with heterogeneous information sources. And somehow the intuition is there already, because these methods can actually deal with non-numerical information by the definition of this kernel. So it's kind of like obvious what's the path to go. The non-obvious part of the path here is, imagine we have different sources. How can we integrate them, all right? And so that's really the challenge here. The challenge really is, for example, imagine that we want to classify proteins according to their function, and we have all these information sources available. We know that the final goal is to design this matrix here, because once we have this inner product matrix, which again is a matrix of, let's say, n proteins by n proteins, which are the data items that we want to classify according to their function here. So once we have this matrix here, we can actually derive, for example, a support vector machine classifier. Now, we want to design this matrix obviously based on all information that we have at hand. And so the big question is, how can we squeeze all that information into that matrix here, okay? So the approach that I'm proposing here to do that is basically an modular approach. So basically, we first want to focus on every single source of information individually and extract the relevant information for that source into one kernel matrix. Once I've done that, I want to design an algorithm that actually can merge all these matrices in an intelligent way. Basically, given the learning problem, try to find the optimal mix of these kernel matrices. So basically, in pictures, what I want to do is for each source of information that I have here, I want to design that matrix. And so that's already like a step forward, because right here we're like basically dealing with a whole bunch of sources of information that are very heterogeneous. While right here we have just a set of homogeneous kernel matrices of known size. Okay, so this already makes it much better defined what we are dealing with exactly. And then in the next step, we now need to find a way to basically merge all these matrices together into this final kernel matrix K that we then want to use for our classification problem. All right. So the advantage of this approach is that we can actually, by splitting it up and basically designing matrices per source, we can focus on designing kernel matrices for specific types of information. So we can just focus on music on a web page. We can focus on images on a web page. How can I extract information into a kernel matrix? I don't have to deal with everything at the same time. The nice thing then is that in the second step, the learning algorithm to merge all these matrices can actually be standardized because it knows what the input looks like. It's just a set of matrices. And so the nice thing then is that we actually also have the flexibility to ignore information which is irrelevant for the learning task. Because obviously we can tell the algorithm, try to discover which matrix of this whole set of matrices is actually irrelevant to predict the topic of a web page. For example, certain sound present on the web page might be irrelevant and we don't need to look at it. Also, it's very flexible. If we have new sources of information that we want to use in this task here, you just basically design a matrix for it and you throw it into the algorithm and you can just rerun it. While if you would take, for example, a graphical models-based approach and you want to kind of model all these sources of information that you have by a huge graphical model, you get another source of information, you need to append something to that graphical model, and you need to rewrite part of the code to actually train the adjusted graphical model, while here you just throw in another matrix. Okay, so to give a couple examples of this first phase now of kernel design, since I assume that many of you already know like how Gaussian kernels and polynomial kernels and so on work, I'll just give a couple examples of these more recent, last 5-6 years kernels that have been proposed to actually deal with non-numerical information. And so first type of information here that we are looking at an example for is, imagine that we have proteins that we want to classify and we look at the amino acid sequences that represent those proteins. So basically the information that we have available about our data points, about our proteins, are variable length discrete strings, okay? So for example, the first protein has an amino acid sequence which is represented here. The second protein has this sequence here. And so now the question is, how can we come up with a good similarity measure between those two proteins, which is based on this information about the proteins? Again, kernel design. And it's kind of nice that we only have to be worried about that question. We don't have to worry, which would have been the case in more classical statistics, about first representing this string of letters here by a vector of numbers, and then we could actually have an algorithm dealing with these vector of numbers. And obviously, by transforming this into a vector of numbers, there is information that could go lost. Or it wouldn't be as obvious sometimes to transform this into a vector of numbers than to say, how can I measure similarity between these two based on the information that I have? Because, for example, here what you could do is you could say, well, if these two strings of amino acids have a lot of common substrings, for example, like here, there's some of these substrings that are in common between the two amino acid sequences, and they're pretty long, then we could say, well, they're actually quite similar. But if we would deal with two proteins that are actually sharing only very short and only very few common subsequences here, then we could say, well, they're actually less similar. So it's actually sometimes very obvious, based on the information that we have about our data, to say whether two data points are more similar or less similar. Why it might be much harder to transform the information into a vector of numbers. Okay. So basically what we're doing here is exactly deriving similarities is designing kernels. Now obviously there's one thing here, which is we have to make sure that that process leads to a positive semi-definite kernel design, because these matrices need to be positive semi-definite. Now it turns out that this type of kernels, which is called string kernels, does lead to such positive semi-definite kernel design. Another type of information that we can flexibly deal with here is, for example, graph-based information. So imagine that the data points we want to classify are the vertices of a graph, and the information that we have about them is the connectivity described by the graph. So this could be a whole bunch of proteins that we try to classify according to their function, and the connections are whether they interact or not. Or a more obvious example here is that these are just web pages which we want to classify according to their topic, and the connections between them are just the links between them, basically. All right. So there is a kernel which is called diffusion kernel now, which can actually be used to establish similarities between the vertices of the graph, so between the proteins or between the web pages. It will establish similarities between those based on the connectivity in the graph, where basically two nodes that are connected with a lot of short paths will end up to be much more similar than two nodes that are only connected by a lot of very long paths. Okay. Now again, this is based on like some random walk process on this graph and so on. There's some math going on in the back, but the bottom line is, again, that by using this philosophy, you can actually mathematically design a similarity matrix between proteins and proteins, or web pages and web pages, that is a positive semi-definite kernel matrix. Okay. Sure. So
let's say you misdesigned one of these kernels. So you take the string one and you use edit distance, which doesn't, as far as I know, lead to a semi-positive matrix. Kernel matrix. What actually happens when you mix it with the others? I mean, so your proof about the SVM would go out of.
Well, it's a really good remark, actually.
How bad is that in practice if you still kind of try to push through the algorithm?
So it's a good remark, and actually it's easier for me to answer it a little bit later, okay. But I'll get back to it. So basically, what we have right now is indeed assuming at this point a whole bunch of matrices that are positive semi-definite, which are designed each of them for a specific source of information. And so now the next step, what your question is actually aiming at, is now specifically how can we design an algorithm that is going to mix all these matrices together in a stable fashion, but also in a way that it's going to tell us which matrices are relevant and which ones are not. Okay. Now the philosophy behind this mixing process is the following. Remember that to be a valid kernel matrix, that matrix needs to be positive semi-definite. Okay. Now it turns out in convex analysis that the set of these matrices that are positive semi-definite forms a set which is called or defined as a convex cone. Without saying too much about it, it turns out it's a very nice set over which to optimize, because it's a convex set. It has a nice shape, and people can actually efficiently or write efficient code to optimize over this set of matrices. Okay. The other thing now is that obviously if we want to optimize over this set, we have to be guided by something to pick the best candidate from here. Okay. So we need to define a cost function to assess, which kernel matrix would be the best one to go with. Now, if we can design our cost function in such a way that we restrict ourselves to convex cost functions, then we have two very important ingredients here for our higher level philosophy, which is we first of all want to learn the optimal candidate from a body or a set which is a convex cone, the one of positive semi-definite matrices. And second of all, we want to do it according to a convex quality measure, which is exactly the two ingredients we need for a technique known in optimization, convex optimization, as semi-definite programming. It's basically an optimization technique that deals with optimizing convex cost functions over the convex cone of positive semi-definite matrices. Okay? So think about it like linear programming, for example, tries to optimize a vector of numbers, which basically just a linear vector, subjected to a bunch of linear constraints. What we're doing here, we're trying to optimize a matrix subjected to the constraint that this matrix has to be positive semi-definite. Okay? And that's exactly what semi-definite programming tries to do.
At this point, you're trying to learn the kernel matrix for a single form of information, or trying to learn the kernel matrix of the combination of other kernel matrices?
Good question. So like at this point, I'm basically just kind of, lining out the higher level philosophy. Now, obviously, this philosophy, which kind of leads, ties into this optimization technique, we want to apply this now to the specific setting that we're looking at, which is we want to use it to integrate the constructed kernels, and we want to apply it for the specific case of large margin classification. All right. And actually, it's good to do this to actually, you could say, let's now try to pick the best kernel matrix for this very specific setting where we have just one source of information, but the problem also is you have to deal with overfitting. So it's actually good to kind of constrain yourself a little bit and not search over the entire cone, but search over a subspace. And for example, the subspace that we propose here is an intersection between that cone and a linear subspace. Okay? Because we want to learn the final kernel matrix K, as a weighted linear combination of these kernel matrices Kj that we have defined so far, or derived so far. So basically those guys are given because we designed them a priori, and those weights eta j are to be optimized, all right? And so what we want to do is we want to learn the optimal kernel matrix for this binary classification problem as this weighted sum, obviously constrained to be positive semi-definite. And this is really where your question now comes in, because obviously if one of these kernel matrices here is not positive semi-definite, because we impose this constraint here, we can just go ahead. Okay? Now, the next thing is that we want to obviously find the optimal k for this specific binary classification task where, you know, large margins are desired. So remember, this kernel matrix, this guy here, will reflect the final embedding of our data points. And now we're wondering somehow about how should we pick this final kernel matrix, which criterion should we use? Now what we know is that, you know, a whole bunch of data points packed tightly together is not going to be good because it's not going to allow us to have a large margin of separation between the two sets of data points. While if we could have a kernel matrix that corresponds to an embedding where there is a big margin between the two sets of data points, that would obviously be much more optimal. So one of the questions here is, can we actually try to optimize the kernel matrix or the embedding such that we have a large margin of separation between the classes, and is that a convex criterion? Now, it's kind of hard to go into the mathematical details of this here, but it turns out that actually trying to maximize the margin with respect to the kernel matrix, with respect to the embedding, is a convex quality measure. And I'm happy to talk after, you know, the talk with anyone about this, why this is and so on, in a more mathematical way. But I decided to omit it here just to not, like, you know, disturb the people that are not really interested in the deeper math of this. Basically, the bottom line is that using this linear combination as a way to integrate the different kernel matrices Ki, and using this as a cost criterion to actually select the best possible candidate K, leads to a semi-definite programming problem, which can be formulated in a form that is actually suitable for optimization toolboxes. And this is basically the results that comes out of, you know, doing some algebra and deriving that optimization problem. So basically, whatever is in the red frame is actually unimportant. I mean, the bottom line just is that this is a semi-definite programming problem. And to illustrate the applicability of this approach to one specific domain, which is a domain that I've worked on quite a lot so far, which is computational biology, I picked out this example here. Actually, I picked out two. The first example is an example where we try to predict which proteins in yeast are membrane proteins. And the reason why we're interested in this problem is because it's actually quite important. So basically, membrane proteins are proteins that anchor themselves in the membrane between, let's say, the outside and the inside of the cell, all right? And therefore, they're quite important because basically, if I'm a malicious virus and I want to do something wrong inside the cell, I'm never going to get in. But I can get all the way to the messenger here, send in the wrong message and tell the cell to destruct itself, okay? If I'm a pharmaceutical company and I want to design a drug to prevent that, what I'm going to do is try to, you know, first of all, know which proteins are membrane proteins, and then design a drug so that it basically goes on top here, sits on top, and prevents anything bad from the outside to send a bad message to the inside. Okay, so it's actually important to know how these membrane proteins look, which means, first of all, we have to be able to identify them. And so about 30% of the proteins in most cells are actually membrane proteins. So we're looking at a quite important class of proteins to identify here. So again, the approach here is quite similar to what I said before. We have a whole bunch of different types of information here, unimportant which ones exactly we are using. But again, so the approach we use here is to design a kernel matrix for every specific source of information. And then in the next step, basically mix all these together using the algorithm that we just proposed. And if we do that, then the results should look like what's coming up soon enough, hopefully. It's coming, I'm sure it's coming, you see. Basically, the vertical axis here are performance measures. So this is an ROC, area under the ROC curve. This is the number of true positives at 1% false positives in these two plots here. And basically the columns correspond to different classifiers. Basically the first 7 columns here correspond to a support vector machine classifier that only uses one kernel matrix. Okay, so basically here this is a kernel matrix based on sequence information. This is a kernel matrix based on interaction information, and so on. And the last column here is basically the result of using the optimal mixing algorithm with a support vector machine, basically using all information to make predictions about membrane proteins. And so what we can see here is that, especially according to this performance measure, also according to this one, although it's less outspoken, we see that there is an improvement of using all information sources by optimally mixing them compared to using only, a single one of them. And so here in the bottom, we can see also what is the weights of the different kernel matrices in the combination, which obviously here are just one, because we're just using a single kernel matrix. Here we see basically what is the relative weight of the different kernel matrices. And so an interesting point here is that, for example, there is a lot of blue stuff in here. And so these three blue kernel matrices here are actually three matrices that are derived from sequence information, amino acid sequence information. Now, if you talk to the biologist, it's actually quite logical that that information is quite heavily used to make predictions about membrane proteins, because it turns out, obviously, that everything inside the cell, there's a lot of water there, while in the membrane, there's not much water. So the hydrophobicity profile of these proteins is very, very outspoken, where you have like a lot of amino acids that like water because they kind of go around in the cell. And then you have like 30 amino acids that don't like water at all because they just go through the membrane and over a very fixed length. So amino acid sequence information is very important in these predictions here. From a biological perspective, it turns out that if we make these combinations here, that there's also a lot of blue in the final combination. So there's somehow, some kind of parallel there. Yeah.
So one of the claims for SVM is it's good at figuring out which of its inputs matter and which ones don't.
Mm-hmm.
So how will this perform if you just say, look, set all the news to 1? Just, make your distance measure be the sum of the distance measures of the individual kernels.
That's a really good question, actually. So basically, this is a question that I couldn't answer very well a couple of years ago when I initially did this research. But now through more experience, what we've noticed is that if you only have 2 or 3 sources of information, then usually it's better to just put all coefficients equal to 1 if you think they're all relevant somehow. And it's not going to make much difference when you fiddle with the weights. When it becomes important is when there's a lot of sources and when quite a few of them could be noise. It's like, if you train an SVM on 3 or 4 features and you have, enough data, then if there's one noisy feature, eliminating it or including it is usually not going to do too much of a harm necessarily. But if you have, thousands of features and a bunch of them could be noisy, then it's better to do a good feature selection because it's going to make your algorithm more stable. Something similar happens here, really. Like if we have a lot of sources of information and some of them could be noisy, then it's good to do a selection and basically have weights involved where some of the weights could go to 0, and actually they do. So they do have a tendency to get sparse. So basically the algorithm has a tendency to exclude. I haven't really explicitly said that, but the algorithm has a tendency to really exclude information sources. So basically in that setting with lots of information and potential noise, it's much better to do this usually. Yeah.
So how will it perform if you add a couple of redundant sources? Will it end up zeroing out those, or will it sort of spread out the mass in the weights?
Well, so redundant sources are a very interesting issue here because so you're looking at a linear combination, and like LPSVMs, for example, have that same problem. If you have 2 features that are a copy of each other, then if you look at the optimization problem, there's no reason why one feature should be chosen above another because it's just a linear combination, so you can exchange them all the time. And so the same thing happens here. So like one of the good things to do would be, we haven't done that yet, but we've noticed there's a problem there's not a problem when there's 2 sources, it's just like their weights are exchangeable, so you kind of like, you should a priori maybe run some code that checks whether these kernel matrices are, quite distant from each other, and if they're very close, then they might just, basically code redundant information and might just want to merge them, sum them a priori before you kind of like, try to assign weights to them. But there's really, because you're looking at the
end up zeroing out weights that are redundant. It just ends up having swappable.
Yeah, that's what's happening. Yeah, basically the sum of the weights of the redundant sources are always going to add up to the same number.
Right.
But amongst themselves, it's like an optimal ridge. You can kind of swap it around, and it's not going to change anything about the optimality.
But they also won't dominate. Like if you keep adding more and more.
No, that's not going to happen. No, because basically, since again it's linear combination, they kind of like all merge together and become only one matrix. And they basically go under the radar of anyone else, and anyone else is like certainly as strong to compete with them.
And also numerically, sorry, do you have to do anything numerically with these kernel matrices? Can they be on different scales completely?
Yeah, so the best thing that I've noticed to do is basically normalize them by basically you center them first, which is always good for stability, because if you have a kernel matrix which encodes interpretability that are far away from the origin, you get entries that are very comparable to one another, and you get numerical instability. So you first basically shift it to the origin just by centering everything, and then you can normalize it by projecting it on the high-dimensional unit ball. And that very often, what that does, it makes a diagonal one. So it makes basically the self-similarity of every data point equal to 1, which is, seems very reasonable to do. Because one of these problems is, think about it, if you have like amino acid sequences that are very long, their self-similarity becomes very high because they have a lot of common substrings. If I only have 3 amino acids as a very small protein, my self-similarity is going to be very low. I only have 6 common substrings with myself. So you want to do that normalization to basically put the main diagonal all equal to 1. And usually when you do those scalings, then these algorithms work the best. So you have basically an equal scale pretty much for all these matrices.
One question, at the beginning you talked about massive data sets. Like how high does the scale?
Yeah, so this is a question, I'm going to answer this like in one slide in a little bit here. So this is another algorithm. Let me just kind of quickly go through it because there is more interesting stuff to say. But basically what we try to do here is predict the function of yeast proteins, yes? And basically there's certain functions that we try to predict. So for each of these prediction problems here, we plot the performance again on the y-axis, and we compare our method, which is in yellow, with a Markov random field method, which is in red here. Okay, and so basically it turns out that we use the exact same data as the Markov random field approach that they developed in University of Southern California. And in the end, for most of these clouds, it turns out that this SVM-based approach actually outperforms the Markov random field approach. The reason why it is, I think, is really because it's just quite easy with kernels to encode information, while if you want to encode everything into some kind of graphical model, it's sometimes really hard to basically use a graphical model to encode certain types of information like microarray information. And so we discussed this, and we think that that is actually the main reason for the superior performance here. But anyway, so one of the good things about their approach also was that they also noticed that if they use all the sources jointly, they can also improve the performance compared to any single source. So basically, in that sense, we had very similar conclusions from independent research. Now, anyway, so there is one slide here, and underneath this slide goes actually a lot of work. Pretty much, I think, the paper that I ever worked longest on in my life. Basically, the question here obviously is having a convex formulation for this classification problem, and is this the end of the story? And it actually is not, because obviously if you use general purpose packages for convex optimization, then they will offer you algorithms that run in polynomial time, which is much better than NP-complete situations. But again, the scaling in terms of the number of data points can be pretty bad. Like for example, here it turns out empirically that it's scaled like to the 4th power of the number of data points, which means that you can basically deal with 500 or 1,000 data points and you're done. Okay. So what we did then is we dedicated a lot of time to look for an algorithm which is actually more efficient here. And based on a similar line of research than what John Platt did with sequential minimal optimization, but also joined with non-smooth optimization, because the big problem here is that this problem is much harder to deal with in an SMO setting than just a regular SVM problem, because this one is non-smooth while the SVM one is smooth. But so it turns out kind of, joining these two kind of ideas or lines of research, that we can come up with an algorithm that actually scales between linear and quadratically in the number of data points here. Okay, and so this is purely an approach that is based on, making the optimization problem itself more efficient. Obviously, the next step now is, can we actually, instead of changing the power here, just, change the n? And basically try to maybe a priori already kind of sample down the data set to actually scale this up even more. But so there is research being done. Actually, very recently there was also code released on the web actually to do this, which doesn't even need any general purpose toolboxes anymore. But so it turns out, yes. So you cannot just basically the general purpose toolboxes are good to just try something out quickly. But if you want to scale it up, there's no way, and you really have to dedicate quite some time to making the algorithm more efficient by using its structure and so on. So to get back to your question now, so basically what I said there is that the linear combination is subjected to a constraint where it's positive semi-definite. So you can throw in whatever you want. There also, if it's negative definite, it'll just make sure that the combination itself in the end is positive semi-definite. Now it turns out that if we constrain these weights to be positive, and we have true kernel matrices which are positive definite, then we actually know that the combination is going to be positive semi-definite already, for sure, because you have a positive linear combination of positive semi-definite matrices. And so that actually allows us to reformulate the problem as a quadratically constrained quadratic programming problem. So we kind of get rid of this heavier SDP formulation, because SDPs are known to scale pretty badly. So that's already also one of the steps that we actually incorporated in trying to get a more efficient algorithm. So in the original formulation, we could incorporate indefinite information. But in the more efficient algorithm, it's not possible anymore since we made this simplification step. So what I want to talk about here is actually, it's a shorter part of this talk, but it's kind of like focusing on another element that I'm really interested in, which is actually coming up with data analysis tools that give you sparse rules in the end, or sparse evaluation algorithms. So just to give an example here, obviously everybody knows principal component analysis, where we try to find a low-dimensional representation of data. For example, a one-dimensional representation that explains most variance of a two-dimensional data set. How this is done is obviously by just looking at the covariance matrix and looking at the eigenvalue decomposition. Now, these techniques, principal component analysis, have a lot of applications in different fields here, but there is one issue with principal component analysis. So it's actually, it's optimal in a sense that it will give us the lower dimensional subspace in the data that explains most variance in the data. It's pretty efficient to compute as well, eigenvalue decomposition. But the problem is that these eigenvectors are very often not sparse, because they're often linear combinations of all variables. So what I mean is, if you have the covariance matrix A here and you write down its eigenvalue decomposition, then those vectors xi here, the eigenvectors, are the principal components and basically are the vectors that construct that subspace that explains most variance of my data. Now the problem is that this usually is a dense vector with very few zeros in there, which means that, in order to explain most variance in my data, think about, for example, you have a whole bunch of gene expression data. To explain most variance in my data, I will have to still involve all the genes, which means that the biologist doesn't get an answer to his question, which genes are most relevant now, okay? Because this xi here is going to have very few zeros, all right? In finance, there's also an issue with this, because these vectors in finance very often are actually related to portfolios that one wants to optimize. So basically, these xi's that I mentioned just before, the weights in these xi's will be used to actually determine in which ratio the different assets should be taken into the portfolio. And if all these entries are non-zero, it means that you need all assets in your portfolio to have the optimal portfolio, which means that you have to pay transaction costs for all of them. So it's also not economically very advantageous to have these non-sparse eigenvectors or principal components. So basically, the bottom line here is that these vectors xi, our principal components, usually have all non-zeros in there, which means we need all genes, for example, to explain the variance in our data. So the fact that it's not sparse gives us lack of interpretation. There's basically no feature selection that happens that can help the interpretation for a biologist, for example. Or we can have cost-driven reasons as well, transaction costs for financial portfolios that would like to have principal components that are a little bit sparser. In image processing, there's also reasons to have actually sparse factors, like for example in non-negative matrix factorization, where it turns out if you can have sparse eigenfaces, that actually the zones that are not sparse often corresponds to very specific parts of the face, like ears and eyes and noses and stuff like that. So basically, driven by these applications here, we sat down and we're thinking how can we reformulate the optimization problem to get the first principal component, for data with a covariance matrix A, but such that it's actually much sparser than when we would just solve this optimization problem, which just gives us, the first principal component, i.e., the maximal variance direction, one-dimensional here in this case, since we just look for the vector x within, some cloud of data. Okay, I guess this optimization problem looks very familiar. I mean, it's just the first eigenvector of a matrix A that we try to determine. But now what we would like to do is we would like to do the same thing, try to find the vector x that maximizes, the variance when we project all the data onto it. We just kind of normalize its length to be 1. But now we actually want to have an additional constraint here, which is that the cardinality, meaning the number of non-zero entries in this vector x here, is smaller than or equal to some number k. So we just want, for example, 90% of the entries of this vector x to be 0. So we really want to enforce feature selection, okay? So basically what's going to happen if we could solve this optimization problem is because we put more constraints on our solution here, we want it to be sparse, well, probably it will not be as optimal. The amount of variance that we can explain will not be as big. That's what's going to happen. Now, besides that, there's something much worse that happens, which is that this problem here all of a sudden becomes a non-convex optimization problem. So if we omit this constraint here, finding the first eigenvector of a matrix, very simple, very efficient. If we add this constraint, which is known as a very hard non-convex constraint, it turns out that this whole problem becomes very hard to solve. It's basically a combinatorial problem that you get. Now, without going into any mathematical details again here, the challenge is, if we ever even want to see how the explained variance goes down when we constrain the cardinality here, if we even ever want to investigate this, we have to be able to solve this problem. So how can we find a solution for this problem? Well, one of the techniques which is known in convex optimization is semi-definite programming relaxation. So basically what you do is you try to find an approximate problem of this problem here using a certain technique, which basically which solution will allow to derive a solution for this problem here, but obviously an approximate solution again. So I'm not going to go into any details of that technique here, but basically the bottom line is that by doing a couple of these relaxations here, we can come up with an optimization problem which looks like this. And basically, this problem here is transformed into an optimization problem of a matrix X again, where the objective is linear in the matrix X. This is just a trace of A times X, subjected to a bunch of constraints here. So again, what we're trying to do is we're trying to optimize a matrix X, our optimization variable, subjected to two simple constraints here, and on top of that, a constraint that this matrix X has to be positive semi-definite. Again, the fact that these constraints are here is just a consequence of all these relaxations that I'm doing here. But the bottom line is that the problem down there, again, is a semi-definite programming problem. So basically, this non-convex hard combinatorial problem here can be approximated by a problem which is a semi-definite programming problem, i.e. a convex optimization problem, which can be solved fairly simple in polynomial time. Okay? Yeah. Oh, there's a conflict of timing here. Okay, I'll get through it in 2 minutes. I'm actually at my final example. So basically, this is just an example showing how the approximation approximates the real problem. So basically, the horizontal axis here is this k value that we put into the optimization problem to constrain the cardinality of our principal component, okay? And so what's plotted here on the y-axis is the true cardinality of the solution. And obviously, we want the true cardinality to be, maximum equal to this value of k here. But obviously, since this is an approximation, it's never going to happen. And so what we see is that this line is still pretty close to the diagonal line, which would be the optimal. It's not jumping all the way up here. So it seems the approximation is actually behaving pretty well. This is an example from finance, but let me give quickly a last example here, which is the example from biology. Basically, the point here is this is a cloud of data, right? It's a cloud of data which is driven by gene expression information. And basically, every dot here is a single rat. And on that rat, we have measured the expression of 8,000 genes, for example. There's 4 types of rats basically corresponding to whether they have a certain disease or not. But the bottom line is we want to visualize that data here, right? Now, to visualize data, what we could do is we could do just principal component analysis and plot the data that we have in a space which is based on the first 3 principal components, which is what we do here. The problem is that these 3 principal components need all the genes to be measured because each of them is a linear combination of every single of the 8,000 genes, okay? Here on this side, we apply sparse principal component analysis. And so the advantage here is that we can actually visualize the data in a way. I mean, if you compare the both, it's not that it's much worse. We can still kind of very easily see that there's different clusters of rats here. But we are able to represent it in a basis where the basis vectors themselves are sparse principal components, which means they're only linear combinations of in total 14 genes here. Which means if now, I tell this to the biologist, he can go into his lab and he can just basically measure 14 gene expressions instead of 8,000 of them to represent this data visually, which is much cheaper and also easier to interpret. Okay. So anyways, the same problem poses itself here. This is an SDP. How can we run this on large-scale data again? So we need to do something special here, which I'm not going to talk about. And basically, this concludes my talk, which kind of talked about these different challenges, including heterogeneous information sources and sparse algorithms for large-scale problems. Thanks.